Okay, so motion, equations and graphs is tied in quite well with the vectors and scalars stuff that you did in National 5. So it's mostly interpreting graphs, but there's also some new equations that you're going to come across that actually I think make life a bit easier than when you did sort of some of the equations in National 5. So remember when you had to calculate or the speed at the bottom of a drop when you're dropping, if you're dropping a stone, and you had to draw a speed time graph, then work out the area under the speed time graph to find out the distance travelled and things like that. I'm going to introduce you to some equations probably next lesson that make life a little bit easier. You don't have to do all those different steps, it's just one equation. So those are some of the equations. Some of them you've come across before. So you've done distance is speed times time, and displacement is velocity times time. V equals U plus AT is just A equals V minus U over T rearranged. And then those three other ones are new. The last one actually you probably have done without thinking about it. It's the average displacement. So displacement is speed times time. Average speed is one speed plus the other speed divided by 2. So that's actually what that equation is. Interpretation of drawing of motion time graphs for motion with constant acceleration in a straight line, and graphs for bouncing objects and thrown up objects, and interrelationship of displacement time, velocity time, and acceleration time graphs. You've done displacement time graphs, you've done velocity time graphs, you haven't done acceleration time graphs, but actually they're quite nice and easy as well. And calculation of things from those graphs. Okay. So, as I said, a bit of revision. Vectors and scalars. Scalars, quantities that are just defined by a magnitude, so just a size, and vectors have a magnitude and a direction. So scalars only tell you, the distance that you've travelled, but they don't tell you where the end point would be. Whereas a vector, you can work out where your end point is. If you say I've gone 10 metres in that direction, then you know exactly where you'd end up. But if you just said I walked 10 metres, you could go that way, that way, that way, that way, that way. Okay. So that's distance and displacement. So the distance and displacement is your obvious vector scalar pair. So distance is the scalar, so distance is just the magnitude, and displacement is the vector, so it's the magnitude plus the direction. So there's an example here of the two different things. So we've got distance and displacement. So we've got a start point A and an end point B. So this person has walked this path here. So we know that they have walked 32 kilometres. But if we wanted to find out where they ended up, the displacement is the distance from the start point to the end point with an angle. And remember, generally, the direction is given as a bearing and it's from north. So it's always good to draw in your north arrow and measure from north to the arrow. Okay. And it's always shown from the start to the end. So the direction is always from the start point to the end point. Okay. So the displacement would be 20 kilometres at 060. So hopefully that's all still familiar from last year. Speed is defined as the rate of change of distance, so how quickly the distance changes. Speed is the distance travelled in a unit of time. And the average speed is given by the equation, average speed is distance divided by time. Okay. And remember the little bar on top means average. Yep. So average speed is distance, which is measured in meters, time measured in seconds, and V bar on the top is the average speed in meters per second. The speed of an object often varies. The speed at a particular instant in time is called the instantaneous speed. So it's like if you're driving along and you looked at the speedometer at that point, that's the instantaneous speed. Okay, and then you might brake and you might be going slower, look at the speedometer, that's the instantaneous speed. So it's the speed measured over a very short time interval or a very short distance, and the shorter the time interval, the nearer the estimate will be to the instantaneous speed. It can be measured using a trolley with a card on it and a light gate, and what you would do, excuse me, to measure the instantaneous speed is you'd use the width of the card. So you just find the speed as that card goes through the light gate. The distance would just be the distance of the card travelling through it, and the time would be the time it takes to go through that light gate. So the instantaneous speed is the width of the card divided by the time on the timer. And the narrower the card, the closer the measured speed to the instantaneous speed would be, because you're measuring over an even smaller amount of time. Okay, so that's instantaneous speed. I think that's sort of from second year and fourth year, third year. Velocity is the vector version of speed. Speed is a scalar. Velocity is the rate of change of displacement. So when you're measuring speed, you're using the distance to find speed. When you're finding velocity, you use the displacement. So velocity is defined as the rate of change of displacement, and it's the displacement per unit time. So as displacement is a vector, velocity is also a vector and has a magnitude and a direction. And the thing that most people lose marks on when they're calculating velocity is forgetting to put a direction. So watch the number of marks on an exam question, because if it asks you to measure to work out the velocity and it's a 4-marker, that gives you a hint that they're going to give you an extra mark for the direction as well. So velocity, we've got a bar on top and the bar on the bottom. This is average velocity, but it's also a vector. The bar on the bottom means it's a vector. You don't have to write the bars in when you're doing your working out, but it's just good to sort of differentiate here. So it's the displacement, which has got a bar underneath it because it's a vector, divided by time, which doesn't have a bar because it's not a vector. And just a fun fact, in case you ever get quizzed in it, V stands for velocitas, which is Latin, and S is for displacement because it comes from the Latin for spatium. So Latin scholars, it's a bit of general knowledge for you. Okay, so an example here. A runner sprints 100 metres north along the track for 12 seconds, then takes a further 13 seconds to jog 20 metres back towards the starting point. So what is their average speed? So you guys have a go at this. I'm sure you can do it. So average speed, remember, it's distance divided by time. So total distance divided by time. And velocity is displacement divided by time. I'll go through it in a couple of minutes. Okay, guys, so I've done the first one already, because it's just distance, total distance divided by total time. You don't have to write the total bit, but sometimes I find it just easy, a bit better just to specify what I'm using. So the speed is the total distance divided by the total time. So I sprinted 100 meters north and then 20 meters back south the way. Okay, so 100 meters and 20. So the total distance is 100 plus 20. And the total time, it takes 12 seconds to go 100 metres and then 13 seconds to do this extra 20 back the way. So the total time is 12 plus 13. So it's 100 plus 20 divided by 12 plus 13, which comes to 4.8 metres per second. Everyone happy with that? So I missed a little bit out on the next one. So the average velocity is the displacement divided by the time. So remember, the displacement is the start point to the end point. So this really should be back here because we haven't got sort of angles or anything. So the displacement is from the start point to the end point here. So it's actually going to be 100 meters take away 20. Yeah. So 100 take away 20. Top. Divided by the same time because the time that it took to do it didn't change. And that should come to 3.2 meters per second. And again, because it's velocity, really we should be putting a bearing, but the bearing is due north, so you could say due north, or you could say a bearing of 0, 0, 0 if you want. Okay, everyone happy with that? Right, good. Acceleration. So just as speed, velocity with the rate of change of distance or displacement, acceleration is the rate of change of velocity. So it's how quickly you can increase the speed or decrease the speed. So again, often you'll get, oh, this car goes from 0 to 60 in 5 seconds, you know, or this car goes from 0 to 60 in 20 seconds. The acceleration of the first one is bigger than the second one. So since velocity is a vector quantity, acceleration is also a vector quantity with a magnitude and a direction. So you've seen it written as acceleration is v minus u over t, but you could also see it as delta v, which just means change in speed, divided by delta t, which means the change in time. Okay. The unit for acceleration is meters per second or meters per second squared. And if the velocity of an object changes by the same amount every second, it's said to have constant or uniform acceleration. So if the acceleration is 5 meters per second squared, the velocity is increasing by 5 meters per second every second. So increasing by 5 meters per second every second. And if you wanted to find the acceleration of an object, you need initial speed, final speed, and time taken. So there's 2 different ways you could do that, and you did these last year, hopefully. So you could either have 2 light gates set up. That would be a roll a trolley with a cordon down a ramp. This would be your initial speed. This would be your final speed, and you'd have to time the time it takes to get between the 2 of them. Okay? Or you could just simply use acceleration. But if you wanted to do it the other way around, that's what you have to do. Alternatively, you can have a trolley with like a double mast on it, a double card on it. So what happens is you can set it up so that when the first of the double goes through, that's your initial speed. When the second of the double goes through, that's your final speed. And your timer can measure the time it takes between those 2, sort of the 2 double cards on. So that's how you might go about experimentally finding it. Speed time graphs again. This page is just taken straight out of the National 5 notes. Speed time graphs can be used to monitor the instantaneous speed of an object. So you can find the speed of an object at a certain point just by looking, right, okay, what is the speed at 25? You can work it out straight away. Calculate the distance travelled by an object. So either by using distance is average speed times time, or the more easy way, area under the graph. And you can also find the acceleration. Are we okay, guys? Look. You got a question? Sorry. You can find the acceleration from a speed time graph because you can find the initial speed and the final speed from a speed time graph. So if you look here, we've got an acceleration here. What is it? It's final speed minus initial speed, so 20 minus 0 divided by that time taken. So let's go through this example. So section A, so we're looking at this part here. The average speed during section A is certain meters per second. So it goes from 0 to 20. Okay, so we've got two known values. We've got 0 and 20. How do we find the average of two known values? Add them up and divide them by the number that there is, so 2. So to find the average speed, it's basically 0 plus 20 divided by 2. So 10. The distance travelled during the section is average speed times time. So 10 times 20, so 200 meters. And the speed of the object increases by a certain amount of meters per second every second. So if it takes 20 seconds to get to 20 meters per second, what does that mean it goes up by every second? 1. Yeah. You could work it out using the acceleration equation. 20 minus 0 divided by 20 is 1. That looks a bit like 11. I'm going to change that. Section B is the rectangle part where it's travelling at a constant speed. So the average speed during section B, the speed isn't changing. So yeah, 20. And the distance travelled is the average speed times by the time. So 20 times by 15 this time, which is 300 meters. And section C, decreasing speed going from 20 to 0 again. So the average speed, again, got 20, we've got 0. Find the average of those. Add them together, divided by 2, so 10. The distance travelled is the average speed times by that time. So the time this time is 35 to 45, so 10. So 100 meters. And because it's only taking 10 seconds to go from 20 to 0, the speed of the object is now decreasing by... Sorry? Somebody say something? 2, yeah, feel free to shout out. I don't mind. I'll ask you a question. 2 meters per second every second. So it's going from 20, but it has to get to 0, but in 10 seconds. And whatever the shape of the speed time graph, the distance travelled is the area underneath the graph. And acceleration is calculated from the gradient of the graph. Because the acceleration equation is actually the gradient, v minus u over t. I want to go through, I know this is a lot of me talking, I want to go through one little bit more about graphs, and then I'm going to get you guys to just do some questions to re-familiarise yourself. So, graphs. Sorry, is everybody copied up? Do I need to keep that for me? So graphs of motion, distance, speed, and time. The following set of graphs illustrates relationships between graphs for the simple types of motion. So you should know what, you should be able to sketch graphs for each one of these situations, for a distance time graph and for a speed time graph. Okay, so I want you guys to have a go. Ignore the acceleration time graph for now. So just sketch in for me what the graphs would look like, or have a go at sketching, and you can do it in pencil if you want, for the 4 scenarios there. So there's one over the page as well. So object at rest, object travelling at constant speed in a straight line, object increasing in speeds and decreasing in speeds. Feel free to talk amongst yourselves and discuss. You done? Yeah. Have a go at, have a think about the acceleration time graph. We done those? Okay, brilliant. Well, if you want to start on questions, but we'll go through this. You can check if you've got it right. You can do it to page 3 of the question booklet.
The jar you give us.
Yeah.
It's not a homework jar.
But I don't really have a separate homework and classwork jar.
Got another jar, so can I keep it?
Yeah.
Can I have a homework jar?
Yeah. Yeah. Right, guys. Okay. So, object. Okay, guys. So the first one, object at rest. So it doesn't really matter where that line is. It just has to be the same distance constantly. So a horizontal line. It could be down here because it could not have set off at all, but it could have set off and then stopped. So it just has to be a horizontal line. The speed time graph one does have to be at 0, a horizontal line at 0, because if it's at rest, it hasn't got a speed. Okay. The acceleration time graph for that one is, again, if it's not got a speed, it's not accelerating if it's at rest. So again, that would just be a horizontal line at 0. The object traveling at a constant speed in a straight line. So constant speed means it's going up the same amount of distance each time. So that should be a straight line. Sorry, it looks a bit wonky. It should be, a straight diagonal line with a ruler. And again, for the speed time graph, it has to be horizontal because it's staying at the same speed each time. But it doesn't really matter where the horizontal line is, as long as it's above 0. And if it's a constant speed, that means it's not speeding up at all, it's not slowing down, so there's no acceleration. So again, we'd have a horizontal line at 0 for the acceleration. The increasing speed in a uniformly in a straight line means that it's going to be covering more distance, so the gradient will be increasing. So it starts off with a lower gradient and sort of gets steeper and steeper. But the speed is increasing uniformly, so that means the speed is increasing the same amount each time, so that should be a straight line, straight diagonal line. And if the speed is increasing uniformly, that means we've got a uniform acceleration, so a horizontal line above 0. And it's kind of the opposite way around for decreasing speed uniformly. So you've got, it's getting less steep, so it starts off steeper and decreases the gradients. I'll put that back up in a second, don't worry. It starts off at a high speed and decreases, but steadily, so it's a straight line. And the acceleration, because it's decreasing in speed, would be, the reason that the axis is written like this is because this is the negative part of the graph. So you'd have a horizontal line below 0, because it's going to be negative acceleration. I'll do that. Okay. Did everyone finish those other graphs? Does anyone need me to push it back up? Okay, and points to note. To find the acceleration from a speed time graph, you find the gradient To find the distance from a speed time graph, we already talked about this, you find the area underneath the graph. And to find the speed from a distance time graph, it's the gradient of the distance time graph. Okay, so if an object changes direction during its motion, then the distance travelled and the displacement of the object will not be the same. Similarly, the speed and the velocity of the object will be different. So those are distance, speed kind of thing. So acceleration is still the gradient of a velocity time graph. Displacement is the area under a velocity time graph. And velocity is the gradient of a displacement time graph. So you just need to watch the wording there. Okay. Does anyone want me to repeat any of that? All that should be revision, apart from maybe the acceleration time graphs. We'll do more on acceleration time graphs later in this booklet. Right, what I'd like you to do for the rest of the lesson is you can either do the little motion revision quiz if you want to, or you can take that home and use it as revision, or you can do the first 3 pages of the question booklet. So all of this is just stuff that you have done before. Yeah, you should be, yeah. Yeah, I'll do that in 1 second. Delson? Yeah. So to find the result.